Good day, everyone. What I want us to consider today is descriptive chemistry of selected groups of transition metals. And we look at their occurrence. Of course, we've already looked at their occurrence and extraction. And remember, we selected copper and iron for occurrence and extraction. Now, for physical and chemical properties, I have selected chromium and copper. So let us start with chromium. Chromium chemistry consists of many colorful compounds. From the word chrome, which means color, chromatography, remember chromatography, and so on. So it's got a lot to do with color, that this metal was called chrome or chromium. Many times you hear people say chrome-plated bumpers for cars or chrome-plated metallic surfaces and so on. So chromium common oxidation states is usually +2, +3, and +6. So the maximum oxidation state for chromium is 6. So chromium 2 is easily oxidized to chromium 3 in air or by oxygen, and it can be seen clearly in this representation, whereby if you take chromium metal and dissolve in HCl, what happens? It will form this complex here, whose color is blue. So that's chromium 2 plus. So remember, it is chromium like that, and it has water on it like that. 6 waters, okay? And we know water is neutral, so it is 0 charge. And chromium there is +2. So the overall charge of this complex is +2. Then, when it is oxidized in air, it gives chromium 3, which is green, that one there. So we shall now go ahead and look at chromium 2 compounds or chromium 2 chemistry. Chromium 2 ion, which is usually hydrated, and usually hydrated and represented by that, has a bright blue color, and it is obtained by reacting chromium metal with an acid, HCl. So in this scenario, you form this, okay? Of course, ordinary chemists, we shall say it has formed chromium like that. But in reality, these metals, transition metals, behave more of in between metals and non-metals. So they tend to form coordinate bonds. So what will happen is that they will coordinate with water first before anything else happens. So immediately they are formed, they coordinate with water, then you get this. So you'll get chromium, you still have chromium 2, but it is surrounded by water. So neutral water molecules surround it. Okay, 6 of them. And the overall charge +2 still remains, and this overall charge of +2 is quenched or neutralized by those 2 chlorides. So in reality, how does that appear? It appears, I'll just summarize on this diagram, on this. So in reality, what this appears like, it is this one, like that, with chloride, 2 chloride ions outside. So this will be +2 there, okay? That's how you shall see later, we shall be representing like that. Then its overall charge, then chlorine, 2 chlorines will be next to this ion and to neutralize the negative charge. So I've done that to save time because I can't go on I will have alternatively said chromium, then H2O. Okay, that's how I will have still written it. 6. Okay, then the overall charge there is +2. Then next to it you'll have 2 chlorine negative, like that. So the whole chromium 2 ion will be represented like that. Well, this is quite different from main group elements, because if it will be sodium, it will just be sodium chloride, and that is it. Nothing else on it. Okay, it will just be sodium chloride, no water coordinated to it, the way we see for transition metals. Now, let's scroll down. Then once you have that ion, it can be further be oxidized by oxygen to form ion 3. Okay, so further oxidation by oxygen to form ion 3. So what does it imply? It implies when we are preparing chromium 2 salts, we need to prepare it in inert atmosphere. So when you're preparing either chromium 2 salts or chromium 2 complexes, you need to prepare them in absence of air or in the presence of nitrogen, so that nitrogen kicks out oxygen. Okay, let's look at chromium 3 compounds or chromium 3 chemistry. So chromium 3 is interesting such that when you put on it different ligands or anions, it forms different colors. And because of that, it is used for making paints and pigments. So it means if I have chromium 3 ion, then on it I put chlorines, I'll find a different color. If I remove the chlorine and put on it maybe water, I'll have a different color. If I remove and put maybe sulfate, I'll have a different color. That's what it means. Okay, so you can vary the anion so that you get different colors. So the same metal ion. So chromium burns in air. When you burn it in air, it will give you a chromium 3 oxide or chromic oxide, which is used for making the pigment chrome green. So again, I'll expect you guys to do the equation. Give you the product which is here, and it's a solid. Chromium oxide dissolves in acid solutions to form violet chromium hydrate ion. And again, we can do that equation easily. Okay, so chromium oxide dissolving. Acid solution. And maybe we can borrow from what we saw up here. Okay, what we saw up here. So when you dissolve in an acid, you bring in the water, okay? Because it's an aqueous solution. So we are communicating in chemistry. So remember, equations are our main tool for communication. So it is an aqueous, but it also has water, okay? So water is very important here, liquid. So that what do we get? Our product will be this one, plus what else? Plus Cl, okay, plus what else? Cl minus, plus what else? Plus hydrogen. No hydrogen this time, okay? Because it is a simple reaction, just like we see ordinarily when you react an oxide with an acid ordinarily. In the main group chemistry, what do? We simply get salt and water, okay? But for this case, we are forming hydrated ions. So transition metals specifically form hydrated ions, okay? Then the anions from the acid will stay outside. So again, let me just do it for the sake of daydreamers. You know, sometimes you teach somebody's daydreaming and he doesn't follow. So I'll maybe try and complete the equation in this limited space. So it is chromium oxide plus HCl aqueous plus water liquid to give us chromium H2O 6 3 plus aqueous like that, plus what else? What is the other product? The other product is your chloride ions aqueous plus, just like that. There's no hydrogen in this case. So once you do that, it's up to you to balance the equations, okay? How many chlorides shall we need? We need 3 chlorides. Why? To neutralize the positive 3 that is on the hydrated ion. When I say hydrated ion, I mean the hydrated chromium ion, which is this one there, this one here, that one. So something very notable is that we have a salt called potassium chromium sulfate or chrome alum, and this is its formula here. Remember, it is sulfate is positive -2, and there are 2 sulfates, so there'll be +4, no, -4, while chromium is 3 and potassium is 1. So this is 4 versus 4 to neutralize the charge. Then there are 12 water coordinated on it. It's a very deep purple compound used for preparing leather or leather tanning. Let's look at compounds with chromium 4 ion, so chromium 6. So we have chromium 6 compounds which exist as chromate ion, dichromate, as well as chromium trioxide. So we have already seen the formula there, chromate and dichromate. Dichromate is just a what? A di, and what we call a dimer of chromate. Okay, it's just a dimer of chromate, 2 chromates coming together. So we go to preparation of sodium chromate, the source of chromate. Okay. How is it prepared? It's prepared from chromite. Chromite is just a mineral of iron, and you heat it strongly in air with potassium, sodium carbonate, and you get your sodium chromate, the oxide of iron, as well as the CO2. So the equation is here. So in this case, we are told that during this reaction, chromite contains ion 2 and ion 3, and both iron and chromium are oxidized in this reaction. So again, if you follow the oxidation steps, so ion from there, this is ion 2, these are ion 2 and chromium 2 in that compound. Then you calculate the oxidation state of chromium here, you'll find it is 3. We know that from high school how to calculate. And the one from ion here will also be +3. And that's why you are saying there is that oxidation. Now let's move on to another reaction. Preparation of sodium dichromate. How is it prepared? It's prepared by heating the sodium chromate in an acid. Mjama, so we look at this preparation of, sorry for the shouting, I was shouting at somebody while I was recording this. So by heating sodium chromate in an acid, you get the chromate oxidized to dichromate. And again, the same story, if you follow the oxidation numbers in the reactant there and in the product, you'll see that very clearly. And we are told this equilibrium is favored by low pH. So if you put more acid, of course, all of us know Le Chatelier's principle. If you put more acid on that side of the equation, it will push it that way. If you put in a base, what will happen? It means the base will be consuming your acid, and therefore the equilibrium will be pushed in the opposite direction. So you need a high pH. Low pH won't help, because if you, you need low pH, that is more acidic conditions. Why? More acidic conditions will be, mean that is a more, and you need to consume that more because Le Chatelier's principle counteracts in the opposite direction. So more of this on this side, Le Chatelier's principle will push the reaction to that side. When you bring in a base, OH minus, what will OH do? OH will react with this and it will form more water, and therefore it will push the reaction backward. So dichromate is found to be a very strong oxidizing acid. And again, you find that chromic acid, which also contains dichromate, is used for cleaning glassware because it will oxidize all these things that will have stuck on your glassware and help you to clean them. So dichromate is a strong oxidizing acid whereby you get your chromium reduced, okay? Your chromium will be reduced from 6 to 3. So this is how the dichromate reacts as an oxidizing agent. And you can see what is happening. And when that happens, it is reduced to that. And this is its reduction potential. So dichromate has a very high reduction potential. Compare this with most metals. Most metals have negative point something, 0.7, like lead. Copper has positive. Copper has positive, I think positive 1.3 or something, positive 0.34. Copper has that. Then zinc has negative that. So look at that. The higher the reduction potential, the more easily it is reduced. So, and the more strong is it as an oxidizing agent. So it is a very strong oxidizing agent. And this diagram just shows you the chromate and dichromate, emphasizing the point that chromate and dichromate are related, such that this is a dimer of the other one. You can go ahead and see how the connectivity happens between chromium and chromium. Of course, you can see chromium and chromium. Then you have your 7 oxygens on it. 7, 7, 7, 7. Those are 6. 6. So most likely the 7th one is somewhere in the middle between the two metals. Okay, the 7th one appears to be between the two metals, like that, something like that. Okay, that's how it looks like. Then it is oxidation state 6. So it has formed more than 6 bonds, okay, on each. Okay, so these are 4. So most likely we have 2 that are double, 2 that are double, then one that is hanging. Okay, like that. And this one is taken care of. It doesn't have a charge. So they are only having 2 charges on this oxygen here and that oxygen there. The rest of the oxygens are double bonded and they are not thirsty anymore. They are satisfied. Let's look at the last compound on chromium chemistry. okay, and that is copper chromium trioxide, which are red crystals and are very acidic. When dissolved in water, they form chromic acid, which is used as an electrolyte in electroplating, such that chromic acid supplies you with chromium during electroplating. The solid is a very strong oxidizing agent, and generally acidic compounds are oxidizing agents. So ordinarily when you see something very acidic, it's a very potent oxidizing agent. And for that power, it also ignites ethanol very fast. How is it prepared? It's prepared when you take conch sulfuric acid and you add to a conch solution of dichromate salt. Then what you get out is a precipitate of chromium 6 oxide as a precipitate. The equation is clearly here. Look at that equation and you can easily appreciate what is happening. It's not a difficult concept here. It's just an interchange of anions. Only that because this is a strong acid, it gives us an acidic salt. Okay. All of us know what is an acidic salt. You can see that hydrogen there. What else do we see clearly here is that it is sort of a displacement thing, such that potassium displaces chromium from its salt, something like that, but it's not really much. But actually what we are seeing is that chromium is kicked out from that salt. Not chromium, potassium is kicked out from that salt. Uses of chromium oxide or chromium 6 oxide, preparing chromic acid, and preparation of chromium metal. So how is it used to prepare chromium metal? That is another story we need to look at. Chromium metal. How do you make chromium metal? Let's see. Before we go to the process of chromium metal, I'm giving you an assignment to go find how chromic acid is prepared. How is chromic acid prepared? That is, I think it's not in this note. So my assignment to you is go find out how chromic acid is prepared using chromium trioxide. Okay, now let us see how you can produce chrome from chromium oxide. You simply react it with aluminium. Aluminium is a strong reducing agent, okay, and it will do the reduction, okay. So compared to chromium, aluminium is a very strong reducing agent. It will take all the oxygen from chromium oxide. It's also used for making steel. Remember, you add chromium to make steel. It enhances production of steel. Remember, steel is stainless iron. How chromium is incorporated in iron to make steel? By reducing chromite ore with carbon in an electric furnace. So this is chromium ore, then you have your carbon, then you carry out the reduction. So what happens? You get two pure metals combined to an alloy, okay? Then your carbon monoxide escaped. So you have just your two together, nothing else, okay? Very perfect way of doing things. Okay, now we are supposed to look at copper. Okay, so what is copper? Copper is a group 1b transition element. Its partners include copper, silver, gold, or its group members are copper, silver, and gold. And it's usually found in nature as a free salt. This is a reflection of the stability of the oxidation state 0 of this metal, and it is a D10. Okay, it is D2, it is S2D9, but stabilizes to S1D10. Copper is not attacked by most acids under ordinary conditions, but reacts with hot, concentrated sulfuric acid or hot, concentrated nitric acid. Why? In these cases, the anion of the acid now acts as the oxidizing agent rather than H plus, the usual oxidizing agent in acids. Okay, so in this case, your sulfate. Okay, for strong acids, they usually appear like that. Okay, so in this case, your sulfate is the oxidizing agent and not the H plus. Ordinarily, most acids, this will be your oxidizing agent, the one that demands electrons. So it demands electrons from metals to give you hydrogen gas. But in this case, what is happening? It is this anion of the acid demanding electrons, okay, from the metal. Why is it so? It's because H plus is a weak oxidizing agent compared to what? Copper metal. It is very weak. It cannot oxidize copper. If you look at the reduction potential, you will find that the reduction potential of copper is very high compared to that of hydrogen. Hydrogen is usually assigned 0, while copper is 0.34. So there's no way hydrogen will reduce copper. Okay. So let's see how this reaction happens. So the two are two reactions for when copper reacts with a conch sulfuric acid and when copper reacts with conch. Okay, with conch with conch. Okay, just a minute. I think I made a mistake here. Okay, so copper can react with what? Hot concentrated sulfuric acid, but also with nitric acid, whether it is conch or dilute. Okay, I hope you're getting that clearly. Copper will react with hot concentrated sulfuric acid, full stop, but also it can react with nitric acid, whether the nitric acid is dilute or concentrated. And that now brings us to these two equations. So the first equation is obvious. This sulfuric acid must be hot and concentrated, okay? So what do we get? We get the copper ion now already oxidized from 0 to +2. Then we get the sulfate ion. Then we get sulfur dioxide. And what else? Water. Sulfur dioxide, of course, will be pairing together with copper 2 to give you copper 2 sulfate, sulfur dioxide, and water. So the products are simply copper 2 sulfate, sulfur dioxide, and water. So that is it with sulfuric acid. It must be hot, concentrated. What about nitric acid? First of all, let's see when it's dilute, because that represents your nitric acid. When it's dilute, that's still nitric acid. What do we get? Oxidation is happening from 0 to +2. What else? We get a gas called nitrogen dioxide. The other obvious product is water. Then when you make it concentrated, what do you get? You get a more oxidized product, which is nitrogen 4 oxide. So compare the two. This is more oxidized, okay? Same anions, but the products differ by the oxidation state of nitrogen. Here, nitrogen is oxidation 2. Here, nitrogen is oxidation 4. So here it's more oxidized. Okay, copper ion. So another thing I want us to note is copper is a transition metal, and therefore in its salt form, it is usually a hydrated ion, as we are seeing there. Hydrated by what? Majorly 6 waters. So we find that in most cases, transition metals are hydrated by 6 waters. 6 waters get to bind on it. Okay. So that is what is there. I want you to study this for a bit. Okay, sorry for the long break. Sorry for the long break. Uh, Copper 1 ion or cupric ion given in this equation as aqueous is precisely copper surrounded by six water molecules, and the overall charge is positive 2. So remember how it is written, okay? So ordinarily it means you have a copper 2 plus, okay? And 6 waters next to it, okay? Okay, something like that. But now, how do we represent? We represent it like that. So don't confuse and say this copper is copper metal. No, it is just copper ion, okay? Because waters are always neutral. So the charge is obviously from copper, okay? Now with that, this salt is usually positive 2. The hydrated ion is always positive 2. And it takes us to something you already know about from Form 1, okay? Hydrated copper 2 sulfate. It's blue in color. When you heat it, what happens? Water is lost and it becomes white. Now, what is the bonding in these hydrates? Ordinarily, the bonding here are covalent or what we call coordinate bonds. So water molecules of copper 2 sulfate pentahydrate are associated uh, with copper 2 plus and the sorry, I am missing my wordings here. 4 of the water molecules of copper 2 sulfate pentahydrate are associated with copper 2 plus, and the 5th water is hydrogen bonded to the sulfate ion as well as to the water molecules on copper ion. So this is how the representation is shown, okay? This is how the representation is shown first, like that. Bonded to the copper. Then the 5th one is hydrogen bonded to both the sulfate and the copper. So hydrogen bonding is something like this. If this is your water, then you have your sulfate here. The hydrogen bond will be between the sulfate and the water, oxygen. Remember what is the definition of hydrogen bonding? It will be somewhere like that. Then also it will be bonded to and it also hydrogen bonded to the other water molecules in copper or that are already bonded. It will also be hydrogen bonded to those 4 water molecules. So water to water hydrogen bonding, we know how to write that. Okay, we can write it so directly. Water to water hydrogen bonding is just an obvious thing we can always write. So if I have another water here, how will the hydrogen bonding happen? It will be something like that, okay? That's how it will. So that is how hydrogen bonding of 2 water molecules will be like. So if people didn't understand it, I'll just maybe distinguish the two with colors. So your water is here, your first water is here. It is hydrogen bonded to the second water, which is here. And the hydrogen bond I've already represented by the dotted lines. For the sulfate and water, again, I've already represented it there. You have your water molecule there, and you have your sulfate down here. Uh, Let's move on. Let me clean the board. What is responsible for the blue color in copper 2 salts? Is it the coordination of or complexing of water molecules? What is the experimental evidence? This is Form 1 work, actually. I think that is directly Form 1 work, and I've already mentioned it a few minutes ago. And again, furthermore, I've gone down here to explain it. So the lecturer doesn't have to say everything for you, okay? You can read it, and that is self directly explaining it to you. The main oxidation states of copper are copper 2, but also we have copper 1. So when copper is heated in air, it forms copper 2 oxide, a black substance at temperatures below, okay, below 1,000 degrees. But at temperatures above 1,000 degrees, you form copper 1, which is red brick red. Brick red. That means it's red in color, almost to the way bricks look like. And it is called cuprite, copper 1 oxide. And that one is an oxide that occurs naturally, possibly due to volcano, because you can imagine what naturally will create temperatures above 1,000 degrees. Most likely is volcano. It tempts me to wonder, are the red volcanic soils full of copper? You can find out, but mostly they're full of iron anyway. So that's a food for thought. Now let us go further into the chemistry of copper ions. A very important biochemical application. Benedict's test for glucose. The experimenter adds glucose solution to a basic solution of copper, and a blue-green solution is left in the test tube. An experimenter adds glucose to a basic solution of copper 2 ion. What does it mean, basic solution? It means you take copper 2 plus, okay, whichever salt, then you basify. How do you basify? By adding hydroxide, okay? Then after that, what next? You add in glucose. And glucose from chemistry, glucose is basically an aldehyde, okay? An aldehyde. An aldehyde, how do we represent an aldehyde? We represent the way we are seeing it there. An aldehyde is simply that with an H and an R there. Then what happens? Your aldehyde is oxidized by copper to give what? Carboxylic acid. So what is a carboxylic acid? A carboxylic acid will simply be the same, similar thing, but now you have that added to it. In other words, it's like maybe the OH comes and attacks there, but it's catalyzed by copper. If you can remember organic chemistry, possibly our OH is acting as a nucleophile. It attacks there, and this one leaves. Okay. So we don't want to go into those details of organic chemistry. But again, if you're doing organic chemistry, you may learn this. If you're doing carbohydrate chemistry, you'll still learn this. And it's a simple reaction catalyzed by copper 2 plus. Okay, and the copper 2 plus itself is reduced. It catalyzes the oxidation, and it itself, it is reduced. So you get the carboxylic acid. So what is the cause of the color? That is the color blue, but the precipitate is your copper 1 oxide. And something interesting that we find in most cases in many inorganic reaction, water is usually a product, a very common product. Another use of copper, it is apart from testing for sugars, copper 2 is used now for testing for sugars. Remember, this is Benedict solution, so you can test for sugars using Benedict solution, okay? Now, the other thing is that we can now use copper as a metal for making conducting material. Okay. Okay, common ores of copper, we've already talked about them. They're mainly the free copper itself, copper oxides, as well as copper sulfides. Now, we having gone that far, so far I can just tell you that we have now looked at the chemistry of two selected transition metals. So I may not teach you lots of transition metal chemistry, but we've selected those two as examples and we've studied it. We've studied them. Now I want us to look at complex ions and coordination compounds. As earlier, ions of transition elements exist in aqueous solutions as complex ions. As earlier seen, ions of transition elements exist in aqueous solution as complex ions. So we've already seen copper exists as this complex. Iron also exists as that complex, and you can see it's hydrated complexes. So what we are saying is that water molecules are arranged around the iron atom with oxygen atoms bonded to the metal by donating electrons to form coordinate bonds. Then you can replace these water molecules by any anion. So if you replace the water molecules in iron up here with cyanide, okay, when you replace with cyanide, you can get that cyanide compound or cyanide complex. So I want just to explain how the coordination happens. So if I have iron here, iron 3, so what happens? Water will be seated here, okay, like that. Water has lone pairs, and these lone pairs will be donated towards iron to form what? A coordinate bond. You need or covalent coordinate bond, not covalent, but coordinate bond. And we know that pretty well from high school. That a coordinate bond is formed by one species that has lone pairs donating it to another one that does not give anything. And you remember what you did in high school, like ammonia. Ammonia has a lone pair, okay? Ammonia 3 has a lone pair. Then if you put hydrogen positive next to it, what happens? It will donate electrons towards it and you end up with ammonium, NH4 positive, okay? The same story is now here again, okay? Similar story, not same, but similar story. Like if monkeys are eating bananas, okay? A similar story is a gorilla eating bananas. Now we move to, and these transition elements have, and their complexes have important biological roles in human nutrition. And these biological roles are played when these metals form complexes, not when they are metal ion. Like if I take metallic ion and swallow it, it will not help me anything. When you are told you are anemic, it means your body needs iron. And you will not be told go and dissolve iron in HCl and drink it. No, you'll be given an iron supplement, which is actually iron complexed to another compound. Then you swallow. Then when it reaches your body, this iron is released and complexed by your biological molecules. Okay. So transition metals are very different from main group elements. Okay. Like if I need sodium in my body, I'll simply take sodium salt direct. But if I need iron in my body, I'll not take an iron salt. I'll take an iron complex, okay? Which in most cases are complex with an organic compound on it. Now let's look at some very quickly. This, we don't need to cram it, but we more of look at what are we more familiar with. The most familiar guy is iron in hemoglobin and myoglobin, because myoglobin stores oxygen in our muscles. Hemoglobin transports oxygen from lungs to the rest of the body. Any other common Any other common metal? Zinc. In alcohol dehydrogenase, it is used to process alcohol. For the guys who take alcohol, that is the enzyme that helps to digest your alcohol. So this zinc, it's not the zinc doing it, it is an enzyme called alcohol dehydrogenase, and this enzyme contains a protein, and that protein has zinc inside complex to it. The same with iron. It's not iron that transports oxygen, but we have something called hemoglobin, which is a protein, and inside there is iron complexed to it. The same with myoglobin. You can ask yourself, why is meat reddish? It's more of the myoglobin inside it, which has iron again on it. So some biochemical substances. So you remember the table is the element responsible in which biochemical substance and what does it do? Glucose tolerance factor, it helps to utilize glucose and so on. So the rest is for you to read. I can't go through the whole list, okay? You can always read it through by yourself. I've just gone for the common ones that we can easily associate or appreciate. Now, how do complexes and coordination compounds form? Okay. Metal atom, particularly transition metal atoms, often function in chemical reactions as Lewis acids by accepting electron pairs from molecules or ions. So metals behave like Lewis acids. They accept electrons. For example, iron 2 plus and water. When they bond, what happens? Iron 2 accepts the lone pair from water as represented here to form a coordinate bond. So I hope we are able to see clearly that this is water, which is donating. Most cases, donors are bases. Remember our base, our ordinary base in high school. It's like that, which is something that has 2 electrons like that. Ammonia, our other base from high school, it has a lone pair and it is a base, okay? So water here is acting as a Lewis base. Lewis bases react by donating electrons, okay? And here we can see now that bond here, water with your iron 2 bonded together. The overall charge of that complex is positive 2. And 6 of them will ultimately bond on water, okay? And we shall see later that transition metals can accommodate as many molecules around it, okay? And most transition metals can accommodate up to 6 molecules, and we call this coordination number. Coordination number, the number of molecules or groups a metal can accommodate around itself. That's why you may be wondering, how come iron is now picking 6 waters? Yes, 6 waters. It is not losing anything. So it's not losing anything. It's just getting water attached to itself, okay? So it can bond as many because it's not losing anything. It's the water that is coming to attach itself. So the same with cyanide. Cyanide has lone pairs from nitrogen, and therefore it will bond using those lone pairs on iron. Apparently, it has 2 lone pairs, one from oxygen and no, one from nitrogen, another one from carbon. So it can use either, but in this case, it's using the one with carbon. Finally, a very stable ion, cyanide, is obtained, which consists of iron bonded to cyanide. The overall charge here is what? Negative. So a complex can either have a negative charge or a positive charge. Okay. So cyanide itself, it's already charged and it has a lone pair. In addition to that, it has a lone pair and it's also charged. So the charge remains as it uses the lone pair for bonding. And that's why 4 of them, okay, actually how many are they? 6 of them are coming. So 6 of them are bringing -6. Then ion itself has +2. So the overall charge will be -4, okay? And that's what we are seeing there. Now, in some cases, a neutral species is produced from a metal ion and anions, like here, okay? We get platinum positive here, coordinating to chlorine negative, okay? That will neutralize that to 0, okay? Then ammonia is neutral. So the overall charge here is 0, okay? The other example is this complex of iron and carbon monoxide. Again, carbon monoxide is neutral, but it has a lone pair. So it will just bond by coordination, and the overall complex here has charge 0 on it. This is something of interest, just something to interest us. Although iron cyanide is a complex like that, the cyanide ions, a solution of cyanide ions contains no cyanide in it because they are strongly bonded, so very little will break out, and therefore such a compound is not toxic. So it is neutralized here. So this compound here can easily act as an acid and combine with potassium to give you that, which is relatively non-toxic, okay? And therefore, can this be applied in detection of cyanide in cassava or cyanide in industrial wastes? Yes. How do we do it? We simply take iron salt, an iron 2 salt, like iron chloride, okay? Then what do I do with it? I react it with cassava solution. I crush my cassava releases cyanide, okay? Then I mix it with the cassava. Then I look for the color change. If there's a color change, then it means the cyanide is coming to complex to my iron salt. The same story, I can take the same iron chloride, iron salt, and react it with something I suspect contains cyanide. Then I see the color change. If there is a color change, well and good. That will be a good indicator that there is cyanide or not. Let's look at some basic definitions. These basic definitions are important for us to understand basic chemistry of coordination of complexes. Okay, so I will just take the next 10 or so minutes to take you through some basics about complexation and complex formation. So remember, if you are interested in complexes, you will study it again under the unit called coordination chemistry. Okay, but for now, because we are studying transition methods, I'll just introduce you to the basics, okay, behind it. So what is a complex ion? Is a metal ion with a Lewis base attached to it through coordinate bonds. Okay, so if I look at a complex ion like copper, why is it a complex ion? Because it has bases. Remember, this has a lone pair, so it's a base attached to it. So this is a complex ion. But copper 2 plus itself, it's not a complex ion. It only becomes a complex ion after it has been coordinated by Lewis bases. That's when it becomes a complex ion. Then what is a coordination compound? A coordination compound is a coordination ion whose charge has already been neutralized. So look at this, it's +2. How do we neutralize it? We can put outside here 2 chlorides, and therefore it becomes a coordination compound. Just like in this example here, the coordination compound is that one, and the complex ion in it is that one. I hope that is clear. Now, what are ligands? Ligands are your Lewis bases that attach to complexes, okay? And they bond by giving out lone pairs. So those are your ligands, the ones that coordinate to your ion, okay? Using coordinate bonding or by giving out electrons. Now, the next concept we need to look at is coordination number. What is coordination number? The total number of bonds the metal atom forms with ligands. The total number of bonds your metal forms with ligands. So, for example, in this complex ion, this is a complex ion, not a complex compound. In this complex ion, how many ligands are there? 6 ligands. So how many bonds have been formed? 6 coordinate bonds. So the coordination number there is 6. We can have a look at various types of coordination number. And again, every metal has its own maximum number of coordination numbers. You'll find that transition metals can form from 2 all the way to 8 coordination numbers, but 8 is not very common. The most common is 6. So this complex ion has coordinated to 2 ligands. The coordination number is 2. Iodine, no. Mercury has coordinated to 3. So the coordination number is 3. Platinum has coordinated to 4. The coordination number is 4. Molybdenum has coordinated to 7 cyanide. The coordination number is 7. Tungsten has coordinated to 8 cyanides. The coordination number is 8. So coordination number depends much on the size of the atom. So if you have a huge atom, okay, remember the groups. So if you go down the group, you get the atomic size increasing. And as the atomic size increases, therefore, the coordination number becomes more. So maybe I'll take you quickly to the periodic table so that you can predict which elements have bigger coordination numbers or more larger larger coordination numbers. So I'll just try and rush to the periodic table. Maybe a more friendly periodic table. Yeah, this one. Look at that periodic table. We expect tungsten. We've already seen now that tungsten is having coordination number 8, okay? Look at that. Tungsten is having coordination number 8. Compare that to chromium. Not chromium. Let's look at something else that we've already seen. Iron. Iron has only 6. Okay. You can see this is period. These are periods. Going down, those are periods. So this is automatically much bigger than iron because this ordinarily you expect tungsten W to be a bigger atom than iron. You see this is a period here, another period, another period. So as you go down, the periods are increasing by 1 by 1 by 1 by 1. So if this one had maybe 4 or 4 energy levels, tungsten has 6, okay? 2 more, 6, okay? So that's why I'm saying that as you go down the periodic table, the size of your atom increase, and therefore the coordination number also is expected to increase. Remember, sometimes things don't happen as expected. That's why I'm saying expected. So it is expected. It might not necessarily be so, but we expect it to happen that way. So having said that, it is now important for us to see how ligands bond. So ligands can bond by one bond, and we call that monodented. So they sort of bite, okay, biting. So we call it dented. So, or they can form two bonds, we call it bidented. So we shall quickly look at this nickel complex. This nickel complex is made of ammonia surrounding the nickel metal, and you can see it is just one bond from ammonia, each ammonia to the nickel. So that is monodented. Each ligand here is monodented. So ammonia is a monodented ligand. Let's go to bidented ligand. And of interest is ethylene diamine, which has two nitrogen groups, and these two nitrogen groups act as our ligand points. So when you put a metal there, ethylene by itself will form two bonds concurrently or simultaneously, and it forms two bonds simultaneously from one ligand. So the whole of this is assumed to be one ligand. Okay, forget about it having two nitrogens, but it is one molecule, and it's just forming two bonds simultaneously to the metal, and therefore it is called bidented. The other one is oxalates. Okay, oxalates, which is ordinarily called oxalic acid. This is more of a model of still ethylene diamine. Okay, this is just a model of ethylene diamine. Okay, it's still here. You can see that this is our ethylene diamine molecule, and it's forming two bonds to the metal. Another ethylene diamine here, two of them. So you can see, instead of me using 6 ligands, like in ammonia, I'll only use 3 ligands. Okay, ammonia, I needed 6, but now I have a ligand that is giving 2 at a go. So I need only 3, like that, to go to my metal. So like that, I need only 3. So the same can be represented like that, okay? And the abbreviation for ethylene diamine is EN. The other one is oxalate. As we can see, the oxalate has 2 Lewis bases. Okay, the Lewis base is there, another Lewis base is there, and therefore that will coordinate to a metal, and that one also will coordinate to a metal there. So oxalate or carbox or dicarboxylate, which is also called oxalate, I'm calling it dicarboxylate, which is also called oxalate, is what? Bidented. Another very interesting ligand is ethylene diamine editor. Editor has 4 coordination points or 4 coordination points in one molecule. Look at that. Those are 4, not even 4, 5, 6. 6 coordination points. So such are called multidented. Okay. Multidented is anything more than 2 is multidented. So this is a multidented ligand 6. So if I put here, for example, nickel, imagine it will all grab one nickel in one go. And therefore it's one thing grabbing one nickel very strongly. So such complexes are very stable compared to one that nickel that is grabbed by 6 ammonia. If you have 6 ammonias on nickel, one ammonia can be knocked out, okay? And it will be unstable. But this one that has just, remember, one nickel, remember nickel can coordinate up to 6, okay? So one nickel just grabbed by one editor. That is very stable because either you remove the whole editor or you don't remove it. So this is very stable. And in many cases, they tell us that polydented ligands, okay, polydented ligands, it's down here, polydented ligands form stable complexes. And these stable complexes are usually referred to as chelates. Chelates. And polydentate ligands are also referred to as chelating agents. and they are used to remove ions from chemical systems. Okay, they are very efficient in grabbing ions and removing them. So you just throw in one molecule of editor, it picks sodium straight away. No, it picks nickel straight away. Unlike if I was to use ammonia, okay, ammonia might not pick nickel, it will take a while. But the moment a nickel moves next to editor, editor will grab it straight away, okay? But if it's ammonia, one ammonia will go there, wait for another ammonia until 6 of them are there. You can imagine that. So applications of editor, let's see the applications of editor. It's used for removing transition metals in food to prolong shelf life. It can be used to treat lead or any other metal poisoning, so that if I take lead by mistake, then I'll drink editor. Editor will grab all the lead, then it will be easily excreted by kidneys, because our kidneys cannot excrete or remove heavy metals from the system. That's why heavy metals will always kill us, okay? So if I feel my system has been polluted by heavy metals, I'll always remove that from my biological system by chelating, okay? And that is why we come in with things called chelating agents, which are usually multidentate ligands. And the best example is what? Editor. So we go to something else. There's this chemist called in a minute, we are almost finishing. There's this chemist called Alfred Werner, who said that metals, especially transition metals, exhibit two kinds of valencies. The primary valence, the one we know from the periodic table, and the secondary valence, which is usually the coordination number, and it is usually 6. So I've already told you about coordination number. So for example, platinum here, okay? In this, okay. In this, my pen has refused to write. In that complex, platinum is +4. That is its valency, primary valency, but it has coordinated to 6 ammonia, and therefore its coordination number is 6, okay? So that's what it means, okay? Then of course, at the end of the day, you'll bring in 4 chlorines to neutralize the positive charge. Other ions of interest are there, like nickel in this other compound here. Nickel there, its valency is what? +2, which you can see from the overall charge when you coordinate it with a neutral complex, a neutral ligand. So here we can easily tell ourselves the valency of nickel is +2. Why? Because nickel is coordinated to water, which is a neutral ligand, so it doesn't affect its charge. And the overall charge of the complex is +2, which means the overall charge is coming from who? From nickel, okay? And the coordination number is what? 6, because nickel has bonded to 6 water molecules. So in the future, when you study complexes, you'll learn something called coordination chemistry, okay? So that is for your future. I want us to conclude with this interesting procedure. And before we go to that interesting procedure, I just want to review how you name ligands. Bromide is called bromo, just ordinarily. Carbonates in organometallic, in coordination chemistry is called carbonato. Chloride is called chloro. Cyanide is called cyano. Fluoride is called fluoro. Hydroxide is called hydroxo. Oxalate is called oxalato. Water is called aqua, okay? Oxide is called oxo. Sulfate is called sulfato. Somehow like Spanola, okay? Now we look at this scheme, which is just transformation of one type of complex to another one. So we are starting with the first complex here, okay, which I want us to follow keenly. We are starting with this first complex, which is just nickel 2+. And it is surrounded by 6 waters, and it is green in color. So we add in ammonia. What happens? Ammonia displaces water, okay? Ammonia displaces water in that complex, and we end up with that, which is blue, okay? Then we put in editor. No, ethylene diamine, okay? We put in ethylene diamine. Ethylene diamine is a more potent ligand. So what does it do? It displaces ammonia from there. It gives us this complex, okay? Remember, ethylene diamine, it's 2. It picks 2 at a time, 2 at a time. So you need only 3, okay? So you get your ethylene diamine complex. On the other side, you can still take this nickel salt and start by adding in sodium hydroxide so that you get insoluble sodium hydroxide. Then you put in dimethyl glyoxime. Dimethyl glyoxime is another ligand which picks, replaces the hydroxide, and you get that, and you can see the color different. So in other words, you can fine-tune your transition metal ions or complexes to the color that you want. You can see I put ammonia, I get blue. I put triethyl amine, I get violet. I put in sodium hydroxide, I still a green precipitate. I put in diglyme oxine, dimethyl oxime, I get a brown thing. So that is how you can fine-tune transition metal elements or ions for different color applications. So far, having covered that, this is what is remaining to be covered. And therefore, in the next session, I will cover this part, okay? I'll actually cover this part. Spectral series, splitting of d orbitals, the crystal field stabilization, okay? And we shall use it mainly, we shall use what we learned in first year VBT and MOT to explain that. And crystal field theory, CFT, is just an extension of MOT, okay? So this will take us maybe an hour. Then once we are done with that, we can go to some extra work. However, this extra work will still be covered under coordination chemistry. So it's not per se the key point of transition metal chemistry, but it can be covered under that unit or that course, coordination chemistry. However, because it's stipulated in this unit, I'll still teach it. And the other thing I want to say that I'm planning to give you a CAT or a continuous assessment test in the next few days. Thank you. Have a good day.